Next thing we're going to look at is how does sodium chloride form? We're going to look at sodium and chlorine in terms of their Lewis diagrams. So let's go back to our periodic tables. Let's write out the Lewis diagram for sodium. Right here. How many dots?
1.
Good. And then we'll go to chlorine. 7 dots. All right, so let's write them down. Sodium has 1 dot. Chlorine has 7 dots. Now, if you don't have colored pens or pencils, here's what you can do. Instead of showing a dot, you can show an X. And so that's how I used to when I didn't have colored pens or pencils. If I wanted to distinguish them from one another, I just drew dots and X's. And the little X means the same thing as a dot. It's just if you don't have colored pens or pencils, you can do that. Now, one of the goals when bonds form is we want to attain what is called the Octet Rule. And in the Octet Rule, you might remember, what does Oct stand for?
8.
Okay, we go back to the periodic table. There's one group of elements that has 8 valence electrons, and that is the noble gases, group 8A. And so it turns out when elements react with each other, they try to attain a noble gas configuration, which is also called the Octet Rule. And that is, there is this drive to wind up with 8 valence electrons. So sodium has 1 valence electron, and so its easiest way to get to 8 would be actually to lose it. Because if sodium loses a valence electron, that is, if it loses 1 electron, it then winds up with 10 electrons, which is the same number of electrons as neon, which is a noble gas. And the easiest way for chlorine to get to 8 is to gain 1. And if it gains 1, it winds up with the noble gas argon. It won't turn into argon, but it winds up with the same electron structure as argon. So what happens then is sodium will transfer this 1 valence electron over to the chlorine. Sodium is happy now because it's given up that 1 valence electron. Chlorine is happy because it's gained that 1 valence electron. If we looked at the atom as a whole, let's look at protons and electrons. If we look at chlorine over here, to start with, how many electrons does an atom of chlorine have to begin with? How many protons does it have? And how do we figure that out? Remember what this number is called? Atomic number, which is equal to the number of protons. So it has 17 protons, and at the start it has 17 electrons. Sodium started with how many protons? What is this number here? 11, which stands for the number of protons, which means it also started with how many electrons? 11. So the number of protons and electrons were the same initially. But now, what happened to the number of electrons here for the sodium? Lost 1. So instead of 11, we now have 10. And what happened to the number of electrons for the chlorine? Gained 1. So instead of 17, it now has 18. So now if we look at this particle here, there's more protons than electrons. So there's more protons than electrons. The charge on the sodium is how many positives? 1 positive. And the chlorine here has how many negatives? 1 negative. And it's 1 negative because it has 1 more electron than it has protons. So what you're going to see me do here is you're going to see me put the chlorine in square brackets. And what the square brackets represent is the fact that we are showing some dots and a charge. So when you write Lewis diagrams, this is what the Lewis diagram for sodium chloride right here. So if you had to write the Lewis diagram for NaCl, This is how you do it. Except when you do it, you'd actually put, instead, I'm showing an X here, you'd actually write a dot. You didn't have it all be the same color. But I'm just doing this for illustrative purposes so you can follow exactly where those electrons came from. But we talked about the importance of balancing charge when we wrote out chemical formulas before, and that a formula for sodium chloride would look like this. It would be NaCl. There's one sodium for every one chlorine. Now what we have formed here is what we call an ionic bond. And an ionic bond is an attractive force that results from the transfer of valence electrons from metals to nonmetals. And it is formed by the attraction of oppositely charged ions. Now, while most of the elements conform to the octet rule, there are 3 elements that are going to form to the duet rule. And of course, the word duet means 2. The elements that are going to form to the duet rule are these 3 elements here: hydrogen, lithium, and beryllium. And that is because of their position on the periodic table. These 3 elements right here will either gain or lose electrons, so they wind up with a total of 2 valence electrons altogether. But otherwise, elements, when they form bonds, will typically conform to the octet rule. So we're going to end the class here by looking at 3 examples today. 3 examples. We looked at sodium chloride. Lastly, we're going to look at our sodium and oxygen. So we want to know this. We like to know, how does a compound of sodium and oxygen form? Then we're going to look at calcium and oxygen. And we're going to wrap up by looking at aluminum and oxygen. So we'll start with the sodium and oxygen. Let's remember that sodium has how many valence electrons? And again, that comes from its position on the periodic table right here. It has that 1 valence electron. Oxygen has how many valence electrons? It has 6. So you put oxygen with its 6 valence electrons, and I'll do these in different colors. Remember that we placed 1 dot on each side before we begin doubling up. So if sodium wants to get to 8, the easiest way for sodium to do that is to transfer 1. So if it transfers the 1 valence electron, it goes over here to the oxygen. Now because the sodium has given up 1 valence electron, its charge is 1 plus. But this oxygen here now needs 1 more. Only way for us to get 1 more is to put in another sodium with its 1 valence electron. And sodium will transfer that 1 electron over to the oxygen. When it does so, the sodium will have lost 1 valence electron, and its charge will become 1 plus. And the oxygen now, whenever we combine dots and we want to show charges, we have to put it in square brackets. The charge that's going to go outside of here is going to be 2 negative. And it's 2 negative because oxygen picked up 2 electrons. And if we had to write a formula for sodium oxide, it would be Na2O is the formula. Any questions on that one?
So do we leave the 2 NAs there, or do we say like Na2 and then?
Well, in the formula we'd write Na2O. If we want to show the Lewis structure, we can write it like this. But your author does actually also show it by putting a 2 in front of there as well to show that there's 2 sodium ions. When I do the accounting like we're doing right now, I prefer to show it like this. And either way is actually correct. Okay, let's do calcium and oxygen. Let's try to do these as quickly as we can. Calcium has how many valence electrons? 2. Good. So it should have how many dots?
2.
Oxygen has how many valence electrons? 6 dots. All right. So easiest thing for calcium to do is to give them up. It's going to give up both of them. So if it gives them up, it's now given up 2 valence electrons. And because it's given up 2 valence electrons, the charge in the calcium becomes 2 plus. And the oxygen now, because it has gained 2 valence electrons, acquires a charge of 2 negative. Well, remember when we talked about the importance before of balancing charges? Well, we have 2 positive balancing 2 negative, and this is why. The formula for calcium oxide would be CaO. And that's it. Then if we do aluminum and oxygen, how many valence electrons here for the aluminum? 3. Good. And again, how many for the oxygen? 6. So we come back here. We write in aluminum with its 3 valence electrons. Oxygen has its 6 valence electrons. The easiest way for aluminum to get to 8 is to lose. And so aluminum will lose it to the oxygen. And if it loses to the oxygen, it can only lose 2 to this oxygen, because this oxygen can only hold 2 more. Because this outer level is now full for the oxygen, the charge on this oxygen becomes 2 negative. But we still have an aluminum that has 1 more electron. So what do we need? Need another oxygen. And that oxygen has how many valence electrons? So now with its 6 valence electrons, this aluminum will give one of those valence electrons over to this oxygen. This aluminum is now satisfied because it's given up 3 valence electrons, so its charge becomes how many? Positive. 3 positive, because it gave up 3 electrons. Problem though is this oxygen needs 1 more. So what do we need to do? Add another aluminum. And that aluminum will have how many valence electrons? 3. So you put in the 3, we transfer one of those electrons over to the oxygen. That's fine and dandy. But this aluminum now has the outer level filled. And because it's picked up 2 extra electrons, its charge is 2 negative. Problem though is we still have 2 valence electrons left on the aluminum, so we need another oxygen. And that oxygen will start with how many valence electrons? 6. So what are we going to do now? Give 2 more. And those are the last 2 we need to give up, because now the aluminum's happy. It's given up 3 valence electrons, so its charge is 3 plus. This oxygen has now gained 2 valence electrons. Its outer level is full, so its charge is 2 negative. Charges are balanced, 6 positives and 6 negatives. The formula is Al2O3. If we asked how many electrons are transferred altogether, it would have been 6, and that's why 6 positives equals 6 negatives. You want to draw the Lewis diagram, you actually get rid of all those arrows. This here is the Lewis diagram for the aluminum oxide. So that's it here for today.